All right, we're looking at examples of Markov chains to illustrate these properties here. And now we're ready for our second example, which will be on 4 states. So that we can draw a little picture here, 4 states, just to visualize. And this will give us a little more legroom to exhibit some other sort of interesting behaviors. So let's just, rather than go through the details like I did in that first example of why the properties are true, for these I'm just going to state the properties and leave it to you to verify them if you're interested. So first we have a transition matrix of the following form. So when you're at state 1, you always have to go to 2. So here you always have to go to 2, with probability 1. When you're at 2, you can go left or right with probability 1/2 each way, and same thing for 3. And then when you're at 4, you have to go back to 3. So that's what this says. And this is called a symmetric random walk with reflecting boundaries. So they're called it's called symmetric because when you're in the middle here, you have equal probability of going either direction, so it's symmetric. And when you're at the edge, when you're at the boundary, then you get bounced off. Like if you're at 1 here, then you have to go to 2, so you sort of reflect off, and you sort of bounce off and you go back. And the same thing for 4. You always have to go to 3. And let's think about those properties here. So we had irreducibility. Is it irreducible? In fact, it is. It's pretty easy to check irreducibility, but it is not aperiodic. So it's not aperiodic, or you might say it is periodic, not aperiodic. And roughly the reason why is because say you start out at state 1, then at odd times, you're always going to be in state 2 or 4. And at even times, you're always going to be in state 1 or 3. And that results in failure of the aperiodicity property. And let's see. Let's think about the stationary distribution. So I worked all this out ahead of time. And this one, it turns out, has the following stationary distribution. 1/6, 2/6. So this is just a simple algebra exercise, not like abstract algebra or anything, just middle school algebra. You just write down the equation that you have to solve, write down. You get some set of equations and you just solve them, and this is what you get. So this is the stationary distribution, so you're sort of spending more time in the middle here and less time at the boundaries. Okay, that was our first little. I'm going to give 3 examples of transition matrices on 4 states like this. 3 variations. So the second variation will allow you to stay at 1 with probability 1/2. Still going to be symmetric. And then when you're in state 4, you have to stay in state 4. So here, so when you're in state 1, you can either stay with probability 1/2 or go to 2 with 1/2. You're symmetric again, just like before on 2 and 3. And then in state 4, you have to stay in state 4. So this is called a symmetric random walk with partially reflecting boundary at 1, and an absorbing state at state 4. So 4, you sort of, if you end up at 4, then you get stuck there. You sort of get absorbed into that state, and you can't leave again. This, it turns out, is not irreducible. And the reason is because if you're at 4, then you can't get to any of the other states with positive probability. So it's not irreducible. On the other hand, it is aperiodic still. It's pretty easy to check. 4, you stay at state 4, so those are 2 consecutive times. And for the others, if you go to 1 and then either just go back, so like if we're here, we go boom, boom, 1, 2, 3, 4 steps, or 1, 2, 3, 4, 5 steps. Both of those paths have positive probability, and those are 2 consecutive times. So, and you can do the similar sort of thing for these others. And so therefore it's aperiodic. And it also has a stationary distribution, which is 0, 0, 0, 1. Again, you just write down the conditions and you can solve for that stationary distribution. And one more example on these 4 states. Let's do one more. So we saw an example here. Irreducible, not aperiodic. And then this one was not irreducible, but it was periodic. And now we'll see something a little bit different. So in this one, you can go back and forth between 1 and 2 here, but you can't get to 3 and 4 from 1 or 2. You can't get to 3 or 4 from 1 or 2. And when you're in 3 or 4, then you can go back and forth between 3 and 4, but you can't go to 1 or 2. So this one, it turns out, is not irreducible for exactly that reason, because you can't get from 3 to 2, for example, with positive probability. It is still aperiodic, and that's clear because from any state, you can just stay at that state at the next time. The diagonal here is positive, and so that's a very simple way to see that it's aperiodic. And the interesting thing here is that there are 2 stationary distributions. So a stationary distribution is not necessarily unique. So we have the following 2 stationary distributions. Both of these satisfy that inequality. That equality, not an inequality. Both of them satisfy this. So the idea here is, you got these 4, and there's sort of like a wall in between. So you can sort of, break it up into 2 separate Markov chains in some sense. Okay, so those were 3 just sort of simple finite examples to illustrate these. And now we'll take a look at a more interesting example. This will be our example 3, and it'll be more interesting because we're going to take an infinite set of states. So our set of states now is going to be all the non-negative integers. And we will consider a asymmetric random walk on this set with a partially reflecting boundary. So we'll take some numbers p and q that are positive such that they sum to 1. I could have put 1 minus p or whatever, but it's easier to write this way. And we will assume that p is strictly positive than q. So like it could be 2/3, 1/3, something like that. And let's write down the following transition matrix. Let's label the rows and the columns. It's going to be an infinite matrix. So from 0, let's say you can go back, you can stay at 0 with probability p, and you can go to 1 with probability p. And the rows sum to 1, so all the rest has to be zeros. From 1, it changed color. Okay. From 1, you can go to 0 with probability p. You can, or you can go to 2 with probability q. And all the rest are zeros. And it's going to be 0, p, 0, q, 0, 0, 0, p, 0, q, 0, 0, 0, and so on. So this pattern we just continue this pattern. So we have this sort of infinite set of states here, and when at any given state you can either decrease with probability p or increase with probability q, except when you're at the 0 state, you either stay where you are with probability p or you increase with probability q. So intuitively, since p is greater than q, you might sort of imagine that things are sort of trending in the sort of downward direction. You know, you're more likely to be moving left than right. And I will just state the properties of this guy. So this one, it turns out it is irreducible. And that's easy to check. You know, I think it's pretty clear. You can sort of probably intuitively just see why that is. You can get from any state to another state. There's some path getting there with positive probability. It's aperiodic, and so we can use the trick. So one thing we can do is use the trick that since it's irreducible, we only need to check aperiodicity at one of the states, and so we can check it at 0. And 0 is satisfies the aperiodicity property because the probability of staying at 0 is p. So and p is positive, so aperiodicity is satisfied at all the states, and so it is an aperiodic chain. You could also check that by starting at any state and then like going, you know, to 0 and then right back, or going to 0 and staying there one step and then going back, and that would give you 2 consecutive times with positive probability where you know, started at that state and ended at that state. So it's aperiodic, and in fact, it also has a stationary distribution, and the stationary distribution is the following. Pi k equals q over p to the k times p minus q over p. And this, so this is for all k, 0, 1, 2, and so on. Again, you know, you just write down the set of equations that you have to solve here. And this takes a bit of work to prove. It's just a calculation, but you know, you have to use like infinite series and set up a recursion and solve for the infinite series and so on. But it's not extraordinarily difficult. And so in fact, this is an interesting example because it has an infinite set of states and it has a stationary distribution. So that's our first part of this example. And the second part, so far everything we've looked at has a stationary distribution, but if we take everything the same transition matrix, same set of states, p and q, all this, except instead of p being greater than q, we say p is less or equal to q. For example, you know, p equals q equals 1/2. Then it's still irreducible and aperiodic. That's not hard to check. But it has no stationary distribution. No stationary distribution. So it's possible for it to have no stationary distribution. And the reason is that the mass is sort of escaping off to infinity here.